Good morning. My name is Fernando Martinez.
And I'm Hugo Casaonda, and today we will be presenting to you an introduction to thin films.
Enjoy. I'm Fernando Martinez, and I'll be taking you through the first set of slides. Thin films can be found in electronics, for example, resistors. There's a thin covering between the resistive material and the conductor material. It's usually a carbon film spiral. And transistors is part of the layering between the N-type material and P-type material. Most of the semiconductors are pretty much built on layerings of thin films. In optics, you can find thin films in window tintings, in mirrors, which we'll be covering later on, and coatings. Thin films are pretty much everywhere. The idea behind thin films is brought up by observing nature. Human skin is composed of layers upon layers of cells that make up your own skin. Cells by themselves are just membranes, thin films, biological films. Also, another inspiration behind thin films is the wings of insects. The tiny membrane that makes up the wing is so thin that you can see through them. Another idea behind thin films is soap bubbles. If you look at a bubble made of soap, you'll see some colors around the contour of it. This can be explained through physical optics. The history of thin films can be traced back a long time ago, but we'll start for 3 centuries ago. It's easier. During the 18th century, Newton, as I mentioned before, couldn't figure out why he can see colors through soap bubbles. He tried to explain it with his corpuscular theory, but he couldn't explain it at all. During the 19th century, mostly towards the end of the 19th century, that's when the Fabry-Perot ethlon was developed for interferometry. Also, during the end of the 19th century, Michael Faraday was experimenting with thin film depositing. The biggest development on thin films was during the 20th century, especially towards the after World War II. Since then, the advent of semiconductor circuitry currently at the 90 nanometer level. But that's a little bit outside of the scope of this presentation. What will be next? We don't know. What characterizes a thin film, besides its obvious name? A thin film is considered to be thin if its thickness is less than 1 micron. Anything bigger than that wouldn't be considered a thin film. This is based on the literature we read prior to this presentation. Though its thickness is less than 1 micron, its width and length can vary. It can be as big as a table for window tinting or as small as a battery for various applications. Some of the materials used for the films are not the same. We can have magnesium fluoride for anti-reflective coating or aluminum for high reflectivity coatings. Like any interaction between light and other medium, there's a degree of polarization. Thin films are not the exception for this. Thin films follow the same Fresnel equations as polarization for most of the objects we've studied so far. There's the degree of polarization of the reflectance on the S and P planes can be determined by equations 1 and 3, where theta t is the transmitted angle, which is determined by Snell's law, and theta I is the incident angle. As you can see, the transmittance of the S plane and P plane are the complements of the reflectance of each of those particular planes. In an ideal medium, there would be no absorption whatsoever. Thin films, since they're really thin, can get away with that pretty easily. As I mentioned before, the interaction between light and a medium will cause a reflection in a transmission of that light. There's also some phase change. The phase change is determined by the boundary condition of the light incident on the medium. There's also some scattering of the light. This is caused usually by uneven surfaces or layers of coatings, or in this case, some non-homogeneous property of the medium. Here's where the fun begins. The reason why thin films were developed was because of their interference properties. Let's take, for example, a quarter wave layer. The reason why it's called a quarter wave layer is because its thickness was assigned to be a quarter of the wavelength of the light it's going to sample. The reason why it's a quarter of the wavelength is because at this particular thickness, it will cause interference with the incident in the reflected beam, which its sample itself. It will become either 180 degrees out of phase from the reflected beams, making it causing a destructive interference pattern, which will neutralize the reflected beam, or the opposite. It could cause constructive interference, which will actually improve reflectivity in certain cases. On the other hand, we have the half wave layer. This layer doesn't really cause any much interference. Half wave thickness will not put the incoming beam out of phase. It's usually used for spacing between quarter wave stacks, which will be covered later on.
My name is UofA, and I'll be taking you through the rest of the slides that we have for you today. Thin film applications. As stated before, thin films have a large field in which they can be applied. For this case, we're going to focus on the optics side of it. For high reflectivity, thin films are pretty much used for mirrors. Mirrors which can have a thin film at the front side of it or the back side of it. The materials vary between silver, gold, and aluminum, which is one of the cheap and common metals, but can easily oxidize, creating irregularities or problems in the optics. Another common application of thin films is anti-reflection coating. They are used commonly on glasses to reduce glare. Filters is another very common use for thin films. We see them on our optics lab, on our daily lives. Examples are beam splitters, edge filters, bandpass filters. What is an anti-reflection coating? Well, it's pretty much a coating which eliminates reflection of a given surface. For a single layer anti-reflection coating, as the name states it, it's a single layer film used to coat an optical surface. And as mentioned before, this property can be obtained by having a quarter wave optical thickness for the thin film. The idea behind this is again to make use of the destructive interference to eliminate reflected light. At the first surface, the air film boundary, we have a reflection, and a second reflection at the second surface, the film substrate boundary, which is out of phase by 180 degrees or pi radians. Therefore, destructive interference will take place and eliminate reflections of that coated surface. Multi-layer anti-reflection coating. It's pretty much the same idea as the single layer anti-reflection coating. The difference is this has a quarter coating on it. The first quarter layer, it's of a low index, and the second one will be of a higher index as compared to the substrate, which could be glass or plastic. But now having the two quarter wavelength layers on top of each other, one being of a low index and the other one being of a higher index, this setup will cause two reflections, one of the film boundary and the other one of the film substrate boundary. Now those two inner reflections, if you want to call them like that, are out of phase together by 180 degrees, which will be in phase to each other, but out of phase to the incident reflected light at the first surface of the air film boundary. In other words, the whole point for this is to cancel the amplitudes of the first reflection of the air film boundary with the other inner reflections. Having said that, we can assume that the multi-layer anti-reflection coating it's probably more efficient than the single-layer anti-reflection coating. As everything else in cost and manufacturing goes, probably the single layer will be cheaper and easier and probably faster to manufacture than the multi-layer. Now to the total opposite of anti-reflection. We move on to high reflection coatings. High reflection coatings are classified in two groups. The first group is the dielectric coating. The principle for this group it's really similar to the anti-reflection one, but instead of using a low-high index stacking, it uses a high-low index stacking. The second group, the metallic coatings. Metallic coatings are primarily used for mirrors. For the reflection, they actually rely on total reflection at the surface where the metallic coating is at. The other possible thing you can have is actually having a metallic coating topped with a dielectric coating. This is referred to as an enhanced metallic coating, also as a hybrid high reflection coating. Now we move on to filters. The first filter we will encounter is the narrowband filter. This kind of filter is made by, again, quarter wave stacks. The stacks are composed of high and low index of refraction. Now the stacking is not as simple as the anti-reflection or the reflection coating. Now because we have more stacking of highs and lows, we're going to be referring to a group of highs and lows as a group, and whatever's in between we're going to call a cavity. The more stacking, the more cavities. The more cavities, according to what we read, the more precision we can get out of that narrowband filter. Now for the narrowband filter, we see a plot here. We can see the one cavity plot and the two cavity plot. And we can see that the difference is quite a bit. You can see more precision on the two cavity plot than the one cavity. But as compared to the two cavity to the three cavity, we can see a small difference, not as big as the one cavity to the two. Hence, probably the two cavity will be enough for some specific application as compared to the three cavity, unless you're looking for a higher precision filter. Now we move on to another filter, the edge filter. The edge filter, it's pretty much what it sounds. It kind of blocks an edge of a spectrum. As before, this kind of filter is made by stacking quarter wave layers on top of each other. But now really the stacking gets a little bit more complex. For the example that we have, it has 41 layers, and at the core we have 25 with 8 layers on either side. The plot for the edge filter. From the plot we can see that from 440 to 600 the light was pretty much blocked all the way. And as before, this filter will only work for a certain amount of wavelengths.
That was our introduction to thin films.
And thank you for watching our film about films.